All right, good evening. I guess I should fix that. Well, so we are here to discuss the NFL Big Data Ball work that we are doing for the Kaggle competition. Where we had left off the last time was we had created an expanded logistic regression model to include a few more fields from the data. Today, we're going to add a few more. We'd also tried doing a few other approaches. We tried using random forests and support vector machines. And surprisingly, they both came back to actually be less accurate in terms of their predictions for whether it would be a run versus a pass play. Now, there are a few things that we need to go through and change up today. I'll talk through that kind of as I go through and review everything that we've done. But we had started by just going through and viewing the data, checking for null data, any missing information. And what we saw here across all of them is that in general, it was pretty much already filled in. So you're already starting in a good place for this project with a very well scrubbed data set. There are a few times where there are row information missing. And then when we looked into those, we saw some of the specific reasons why. So this was the yard line side. 224 rows had no data in them. The reason for this is that these were plays at midfield. So the ball is not in one side versus the other. It's in like a neutral part at that 50-yard line. The offensive formation and receiver alignment, these were kicking plays, so they did not count towards here. So that's why they had no data. The play clock at snap, there was one row here. It basically just was negligible. It just was missing information, but you could infer it from the row before. Pass result and pass length. The reason why these are not or don't have data in them is because these are run plays. So when it's a run, there won't be a pass or kick. You won't have pass information there and so on. You're not always going to have this from Pro Football Focus, an idea of what like some of the defensive assignments and concepts are. So those have more rows where there is not information, but we're not using them for the purpose of our model. And in general, it's got a pretty good coverage. And then we started to look at some of the plays, and we quickly realized that you can't just take the mean of all the player plays for the rushing yards. And the reason why is because on a given play, if it's a rush, only the quarterback will have rushing yards. This means that if it was a pass play, there was no data for all 22 players on the field. If it was a rush play, well, then 21 of the 22 players on the field would not have rush yards. And so what you see here is you get a very, very small number overall for the average rush. But then we found that there was a flag field for had rushing attempt where that was equal to 1 and meant that the player was the rusher on the play or had attempted to run. So once we filtered to that, we got to an average about 4.5 yards per rushing attempt. Oh, sorry. And then similar things happened for receiving. We originally started these side by side. We also found out the pass reception field. Now, this is something that is what we're going to go back and improve upon in the data set today, because had pass reception does not mean that the pass was not attempted. And so when we want to know the average outcome on a play, we can't only have the plays that had a pass reception here. So that's part of why we'll need to go back through the play data and figure out the aggregation information. So then we tried to do some grouping in our data. The first one here is just by the team, and then we added to it a sort. This one is looking at basically the top 5 teams. So very similar to here, this is how we got the rushing mean yards mean, this group by has to go before this. We are grouping by the team abbreviation field, which gives you that. And then the sort here is putting them in order. If you don't put anything here, it will be ascending true. And so what that means is that you will end up with the bottom teams first versus the top teams, which is what I wanted to see here. So we saw the top 5 teams: Chicago, Las Vegas, Seattle, Jacksonville, and Baltimore. And then the reverse of that, the bottom 5 teams. So we had Tampa, Los Angeles, Indianapolis, Cincinnati, and Denver. And we did a similar thing for pass reception, just only doing the top one just to give you an idea. You can change this if you want to see the bottom 5. Then I started to go through and generate some ideas. So maybe instead of averages, we also need to see how many rushing attempts by teams. Were there fluctuation there for the individual teams across the season? And then starting to kind of group these and pull them together. And this has been expanded upon greatly. We took the player play information, but then we also added in the player's actual name instead of just being the NFL ID here, as you can see kind of what this looks like. And then getting an idea of the offensive formation information. And then we also included, here it is, the pass result, the receiver alignment, the quarter that the play was in, what down it was on, the yards to go, the home and visitor score, and then the yard line number on the field. Now, the absolute yard line number here means the yards in relation to the end zone. So you can imagine when you're watching a football game, when they're in the red zone, that means the absolute yard line number is 20. But if you're on your side of the field after the kickoff, your absolute yard line number is 75, because you have 75 yards to go until you get to the end zone. So those were all the fields that we pulled in, and then we had done just a little bit of, and I see the issue here. A little bit of work here to also include the home team abbreviation. The reason why that is important is that when we get a little further down here, that is actually how we calculate out if your team is leading or behind at the time. And that's a field that we had also included in the model, because you can imagine if you're down by 2 scores in the 4th quarter, you're not going to want to run the ball as much because that uses up more of the clock. But then if you're ahead by 2 or more scores, you're going to want to try and run just to use up use up that clock and try and maintain your lead. So going through here, we started to this is before we had put together the models, look at the information a number of different ways. So we looked at the number of rushes by formation. This is the average versus the mean. One of the interesting things to note here is that the empty formation was run from only 95 times, but looking at this, it was the most effective. But the reason why is that if you look down here a little more, for the most part, when you're in an empty formation, you're going to be throwing. And so the defense is playing more to prevent the throw rather than it is, or not prevent the throw, guard against the throw, than it is to guard against the run. And that's why, even though they were infrequent, they were effective plays. A similar thing here, but actually in the opposite, the Wildcat formation had a below average rushing yard outcome. You can see here it was only attempted a few times, but if you look here, it was only ever passes attempted out of the Wildcat 10 times on the season. So teams knew that the run was coming, keyed against the run, but the offense couldn't take advantage of it, right? Because in a Wildcat formation, this means instead of your quarterback receiving the snap, it's a receiver or a running back taking the snap. And that is way less likely to have a good passing outcome in terms of it was only completed 10 times. And so we started to look at individual teams. I threw Arizona in here just to prove out that we could do the filtering this way. But then when I went back, we decided to take a look at Tampa Bay, who had the worst rushing yards per play, just to try and get an idea of what was happening here. And what I saw ended up being the case. You can see here, sorry, I think this is a little out of order. We were trying to get an idea of like who the best receivers were in certain formations. We kind of proved out that we can do that, but it was so infrequent during the games that it would be really hard to predict an individual based on their formation by game. Coming down here more, this was a breakdown on the average rushing and receiving yards per game. And surprisingly, a number of times the empty formation came back with like no rushing yards. It was only ever used for receiving. But the average here is like a whole number, so only a few passes were ever attempted. Sorry, not attempted, completed from the formation, and you can see kind of that breakdown by game. But this was where we started to get into more interesting. So basically, what this shows us is that Tampa Bay, based on their formation, was heavily tipping off whether it would be an actual rush or a pass play. So here you have 15 rushes out of the single back formation, only 2 ever completions. Not 2 ever. In this game, only 2 completions. And then the shotgun formation, there were 7 rushing attempts, and there were only 12 plays completed. As we go into more games in the season, you can see more completion, more passing completions from the shotgun formation, and almost every time single back would be when they were actually rushing the ball. So you can see there's a few here. This game's a little bit anomalous in that they actually ran more out of the shotgun, but in general, it was heavily favored to running out of that single back formation. So then we started to build out the basic models with the initial data. What we had available to us, this is the enhanced data set here. What we had available to us was basically everything up onto this receiver alignment. And we were trying to pass that information to the model. So we basically only gave it 4 fields. What I did was I used rushing yards as the field to identify the flag. So if it did have rushing yards, then I would mark that play to a new binary field called rush. It would be 1 if there were rushing yards, 0 if everything else. Then we gave the model 3 basic variables and tried to tell it, could you predict to me if I'm going to rush the ball? First was the formation that the offense was in, what team that it was, and the receiver alignment information. Now, it's a very, very simplistic model, but the goal here is because we're trying to predict what happens post-snap based on the pre-snap information. All of these you could be assured of before the play had started. So you would have the line formation for the offense. You knew what team you were going up against, and you knew how their receivers were arranged. Now, there would be some cases where there are motion, and that's why we're wanting to add some additional information to our model today. This is the process that we go through here. We're splitting the data set. We're using 80% for the training. We're holding 20% out for the testing. We're using the one-hot encoding for all these categorical variables. So team abbreviation is pretty straightforward. You would have 1 for each team. Same thing here for the formations, 1 for each formation of the team across the whole data set, and then the receiver alignments. I think there are like 9 buckets total that it could be in. But for the most part, not too wide of a matrix once you actually put them in this one-hot encoded version, and then run a logistic regression. There's no fancy training or anything, so just a very bare bones model. But do your prediction, and then just give me a basic accuracy score. What were the actual play outcomes versus what the model would predict for those. And then you can see here the model accuracy was actually 70%, which is a really good start on a model here. So we have good data. We have a very good basic model. The idea here was to try and give it a few more pieces of information. So last time when we worked through, we added the quarter, the downs, yards to go, the score differential, which we'll talk about here, and then the absolute yard number. Basically the distance when the ball's snapped, how far is it from the end zone? So this is the score differential. Basically, we were just checking to see who the home team was in the game, if it matches the abbreviation for that team. If that's the case, then we are taking the home score minus the visitor score. So if you're the home team, home minus visitor. If you're not, which means you're the visitor, you're going to do visitor minus home. And so that will give you the score differential at the time of the play snap. Then I took the yards to go and put them into 3 very basic buckets. Anything more than 7 yards is going to be a long distance. First down will always be long. Anything that is 3 or less yards will be a short distance, and then all those in the middle are the middle. So 4, 5, 6, and 7 become the mid. Then for the distance bucket, I took that absolute yard line number and split it into 3 groups as well. Short here is basically just the red zone. If you have 20 or less yards to go, then you have a short distance left to go. 50 basically was the number I had estimated for the cutoff for a kicker in terms of the long, and then everything else would be that middle ground. So between 20 and 50 is your middle bucket. Then we go through all of these as categorical variables. Even though quarter and down are actual numbers, for the purpose of the model, they are categories. You can't have a 1.5 down or 2.5 down. It's just not possible. And so you don't want the model to start to make assumptions based off that. And so we're treating them as categorical. What that means here is that the first quarter is always, 1, 2, 3, 4 in the data set, but they're actually categories. And there's a difference in how you're going to treat the game with a quarter to go versus, versus the first quarter versus the fourth quarter. They're going to have completely different ways that you're playing based on the game and the situation. Same thing for the down. You're going to play a little bit differently on first down than you are on third, where you're trying to make sure that you convert. The last thing here is those buckets that I just described, the yard bucket and the distance bucket. And then using the score differential as a numeric variable, right? There is fluctuations in the scores. You can only have whole numbers, but it is a number. You could theoretically make this a bucket if you wanted to change it to like field goal, touchdown, 2-score game, 3-score game, etc. If you wanted to treat it that way, we just did the score differential. No need to put any buckets on it. As far as the variables go here, it's just this the full list of the categorical and numerical variables, and we're still targeting that rush field. So is it going to be a rush play versus a pass play? Same thing here, splitting them out into 80-20. We do have to enter now a standard scaler. What this means is that the standard scaler means that you have a mean of 0 or an average of 0 for the number here, and then a standard deviation of 1. So the idea here is that everything is scaled down as much as possible to kind of keep it more uniform here. And then, yeah, this actually explains how the standardization here is. So We then put that into the pipeline. We did have to add this line here of making it just a linear solver. What was happening was it wasn't converging once we had added any fields beyond these first three. So we added that here. It's still a very basic model overall, no real hyper tuning or anything like that. Just trying to get a better idea of how we're doing. And then we saw that we actually got up to 73.1%, which is pretty good considering we only added a few fields. We didn't lose any predictive power in terms of accuracy. We actually made the model more accurate, which was nice. Then I tried a different version just of treating the yard line number and the yards to go purely as numerics. So hold on, let me run back. Oh, sorry, I forgot that these are not on. Just run through these real quick, and it will be quick. Go through. That's 73.1. Now we are treating the yards to go and yard line numbers as numbers. And you can see here that actually took us back. So they were better off being bucketed into those groupings rather than them just being treated straight as numbers. And the reason for this is you'll see this more and more as you watch football games, especially when it comes up to fourth down. You'll see like go for it or punt. And a lot of times what you'll see is in those short yardage situations of 3 or less yards, once you're on the opponent's side of the field, it actually starts to tell you that you're better off going for it versus punting or kicking, because it's more likely to lead you to a better outcome. And similar situation here starts to occur when you're treating them as individual numbers and scaled. It kind of loses some of the context that is a little bit different from what you're getting in the game. Then we also tried a couple other models. This was back with the very basic predictor. So we had this go through the pre-processing category. What we had actually seen, and right now it's going off of the categorical variables that we have set here, where we're getting a bit different outcome, but this needs to be updated to support the new categorical fields. So still going off of categorical, it's going to need to use variables, but instead of the pre-processing step now becomes this across these models. Why did that not do that? Copy. It'll take a little bit longer for it to go through. You can see here now, both models have actually improved versus before when we were treating them just with the categorical variables. By adding some numbers, we did get improvements in these models. So this one's very nearly 70%. This one is 70.7%. But in general, if this were me, I would be, I'm just going to change it to use this one now and see if it makes a difference. So go here. Why is it not part of the database? Here. Okay, because this one does not have the split before it. So if we want that to stand alone on its own, so there we go. And you can see here, the bucketing here actually hurt the output of the random forest model. It decreased from 70% back to 68. And then SVC was not really affected by that change at all. So a little bit surprising to see here is that random forests prefers the numerical information rather than us using the buckets. And then SVC wasn't really affected by it. SVC is just support vector classifier. It's part of the support vector machines models. It's just the classifier version of it because we're only trying to predict run versus pass, right? So we're giving a very clear classification. We're not trying to predict the yards gained or anything by that on the play. So we have very basic models, but like I said before, we have a couple things we want to get to as far as the changes to the data set that we want to make. We want to, let me go here, I'll share out. This is the list of fields that we have available for me, or for us to work off of. This is based on the Big Data Bowl. And there are two fields that I was interested in. They were the motion fields. But that's going to be a per player, huh? Okay, so we will need a play motion field, or a way to create a play motion. The idea here, was there motion on the play? And this is, I'm pretty sure this was the player play field, right? Player play data. So we want to go off of player play. And then player play motion since line set equal and I want the play ID the game ID and the play ID, because there's play ID can be across can be the same across multiple games. So we need to do that to enforce that part. And this is wrong here, equal to 1. These are the fields that we want to, and we want to group by, this is the game ID, play ID. Doesn't particularly matter why. We're going to call this play motion. It's not inner join, it's a left join. Because I want only the data that's in the enhanced data set here. Every play is not going to have motion. If we left it as an inner join, we'd massively decrease our data set. The reason why these could be inner is because every game has to have a host team. Right, and then the same thing here. When we're joining this on the data set, it has to have these information. So that's how we can get away with doing that there. And then this can be a left. Theoretically, this could be a left join too. It really doesn't change much. And might be better for the data if we had it that way. So let's just do that. Oh. Play motion. Same thing here. And then play motion. For row in range, minus play motion. If play row motion since basically, if multiple players were in motion, we're just setting it to 1. The idea here is it's just a binary field. It should be 0, 1 for the outcome. Did I do it the right way? Did I? Let's take a look at why this is happening. Play motion should work. What does play motion look like? Yes, there's 679 rows where motion since line set is actually greater than 1. So what is it now like in here? Oh, it's because the index here. Yep, and that was the issue. Now we're at 0. Perfect. Okay. So that was a mistake on my part. The reason being it had 2 indexes, basically the game ID and the play ID. And then without those, trying to pass row as a single index would cause it to error out. And that's why we were seeing the error 0. So then we can just merge in this information now. Perfect. Same length as before. Bring that all the way down. And so we want motion this line set. Adding that here and also in the variables. Yard bucket distance. Oh, because I did not rerun this. Every time I recreate the dataset, I have to do that. Rush doesn't exist. Where are we, Rush? For next time, I'll have to go through and do a little bit of work here, just cleaning up and making sure everything's kind of all in a row. And now, did I do this? No. So here we go. Adding in the motion, we actually predict or are able to a little bit more accurately predict the data. So we've gone up from 73.0 to now 73.8. So another small increase here just by adding another field here. And then let's see if this, because remember there's like a play on the interactions of all of these. So now if I go here and I try and say to tell me the difference here, you can see we actually got a lot more predictive power when we were treating these as numbers instead of using the buckets. And so we've actually caused this to go up to 74.3. So this was 72. So we got almost 2 percentage points now by just being able to identify motion at the play. Sorry, so you understand a little bit more on the combinations that you can get here just by adding in the simplest, well, not simplest, but another thing is if there's motion on the play, we're able to more correctly predict run versus pass. And so I would be curious if that's just because if there is motion, it's more likely to be run, or maybe at a certain formations that is the reason for the case. But that was a pretty big jump for just a singular field. And again, the idea here is just to go, we're going through that data, the data field list that I had linked out, just to try and get an idea of what's happening on the play. So we're not even looking at the individual players in this. We're actually only looking, if you go back up here to how it's grouped, based on purely on the play information. So our grouping is on the game ID and the play ID, and we're not passing the player information even to the model. All we're telling it is what is the alignment on the field, what is the down distance, the distance not just in terms of getting a first down, but also the distance from the end zone, the time in relation to the game, right? Like what quarter it is, the motion since line set, and I'm curious if we can get even more lift if we can find the game clock information. So player play. ID version temp. Time. Not the individual timestamp of the play. Start game time, game clock is the field. And that is in the play data. So we're gonna go back up here. What do we have right here? So game clock is in the play data. I'm pretty sure. Plays. Yep. Go here. And now we're adding in the game clock. And so there's a few different things that we can do here with the game clock. Tying this together with the quarter gives you an idea of the time remaining in the game. So let me put that together. Oh, because I added it here. That's because it's not game underscore clock, it's game clock. So remember to reset rush. Reset this score differential. This is the yard bucket. This is now time remaining. So for each row, if quarter equals 1, oops, and we're going to need to do this for each quarter. So we're going to call this game time remaining. It's going to be like a two-step process to get here. So it's minutes, second. I can think of how to quickly do this in SQL, but this is Python. I need our data enhanced at row game clock. this is why it gets convoluted. So I have to do string to int is just casting here. But this is the first two digits plus 45. But then this plus, and this whole thing. From character 3 onward. So we're taking the game clock. We're cutting off the first two digits, changing it to an int, adding 45 to it, converting it back to a string, and then using string concatenation, which also uses a plus sign, to basically stitch those two back together. Yes, it worked. Okay. So now I just want to quickly see game time remaining. A lot of them should be nulls. Great, none of numbers, perfect. Okay, let's, before I go start and think that something is severely wrong, we're going to do this for the other recorders. Now, if it's quarter 2, we add 30. If it's quarter 3, it's there, and then else. This one is the most straightforward of them. Because it's literally just the game clock. All right. And let's see. Yeah, that's what I afraid was going to happen. Well, just get everybody on the same page. So now you know the game time remaining. Right? We have an idea based on this how much time remains in the games. But we also want to think about this. There are specific points in the game where it is very useful to know how long is left. So there's a huge difference, right? We call them 2-minute warnings. 2 minutes before the halves are those situations where the game is a little bit different than it was before. So I do want to create a bucket here for even if we do just the 2-minute warning scenarios to see if it that is the reason for that. So starting with the very same process. If is greater than bucket. TMW, 2-minute warning. Else, it's nothing. If int oh, yeah, that's going to be much different situation. So there we go. 488 plays where there's already less than 2 minutes in the halves. And now let's just take that think about it for a second. Is there anything else we would want to keep in that time bucket? Two-minute warning. Oh, there's a second group here that we're missing. Right, this only captures the two the 2-minute warning at the end of the game. But there's a difference here where it's got to be less than 3,200. This way. So there we go. Much bigger group. And that makes more sense now. So, right. That's actually 4 minutes in the game, but that should be a 4 over 60, about 1 in 15. And we're roughly there, if not quite the same, because they do use timeouts to try and get more plays called in that time. So that gets me closer to the 2-minute warning. So now I want to go here. Add the time bucket. So we increase that slightly. Time bucket goes here, here as well. All right, so we're approaching 75%, which is great work. So we went from 73% to almost 75% in a little over an hour. Again, we are using only the key information that we would know before a given play. So we know in the offense's formation, the team, the receiver, quarters, down, motion, and then a time bucket for the 2-minute warnings before the halves, only those. Theoretically, I think there could be a secondary bucket here that could go up to like the 5-minute time frame before the half. Actually, I don't think about doing it before the half. I may think about doing that before the end of the game. So maybe the final 5 to 10-minute time frame, where teams really have to start changing their approach. Right? If you're down 2 scores and you have the ball with less than 10 minutes to go, you've got to treat the game differently. You cannot have an 8-minute drive and then take the onside kick it and do that. You got to try and play to score quickly, give your defense a chance to generate a 3-and-out, and then use that short field going again. Right? So come back up here to that time bucket. Let's just do this. Let's call this FTMW and then HTMW. So final 2-minute warning, halftime, or half 2-minute warning. I'm going to call this I don't even know, but this should be a situation where we're now under 10 minutes remaining. Right, but you can start to see how this would come together, because if there's a 10 minutes left and I don't know, the game score is more than 8 points, you're playing the game differently. So what one was that? Score diff. Let's take this. And or this is that's one. It's 2. let's see if this works. Invalid syntax. All right, what is the yeah, it's the just this there. Open, open, close, close. That's fine. Open, open, close, open, close, and close. Oh. There we go. So number of times where there is a 2-score scenario is actually surprisingly high. But now I'm curious if that actually helps us at all with our time bucketing. 74 actually decreased slightly. Yeah, so we actually decreased our predictive power by even caring whether it was a 2-minute score or not, which is surprising. So I just want to see. Should change it slightly. That further decreased it. I imagine it's going to be the same for this model too. Ooh. Oh, it went up slightly. Not much though. So knowing whether it's the final 10 minutes or was 10 minutes in the 2-score game, it didn't actually matter, or it didn't actually positively impact the model. Right? We saw that it ended up decreasing our score as we were almost right up against the right up at the 75% mark here. So kind of surprising that that would be the case. Now this is rerunning random forests with the second model here. So treating the yards to go and the absolute yard line numbers as numbers instead of using the buckets. And you can see here, random forest is now starting to gain on the original logistic regression. And the same thing here for the SVC classifier. So before there was like a 2 or 3 percentage point difference between those, but we're much closer to getting more predictive power as we continue to add in more fields, where something like a simpler logistic regression is starting to get caught up on by the other models. But the nice thing about the regression is you can deconstruct the model to give you like the exact scenarios where it would be way more likely. You just have more visibility with the logistic regression to understand the impact of the different fields here. And so this would be something that would be more useful to a non-technical audience, because you can simply say, let's say you're going up against Tampa Bay, as we saw it, right? If it's the first quarter and they are in, if it's the first quarter and they're in the single back formation, they are going to run the ball. We know, even just from the simple numbers before, it was 80% of the time they run the ball from that formation. But let's say in the first quarter, they're actually even more likely. The model would tell us exactly what percentage that would be the case. And so I do like that we are getting more power here. 75% accuracy means, what, 3 out of 4 times you're going to know correctly what the play is, just based on the information that you have before the game, or not before the game, before the snap of the ball. So it's just like knowing more about the situation is very powerful predictively in terms of what they're going to do. Right, so I think this is where we can leave it here for today. We did add the motion flag and then pulling out some of the information in terms of the time. We did try 2 different experiments with the time. One was just knowing whether it was before the half for the final part of the game and halftime itself. It didn't matter that we originally had these grouped together. That didn't matter as much. We had tried putting in another bucket here for when there's less than 10 minutes left in the game versus less than 10 minutes left in the game, and your opponent is a 2-score game. So there's more than 7 points difference between the 2 teams. Right? Yeah. I was just trying to remember what it was. Yeah. So if there was less than 10 minutes remaining in the game and the score differential between the 2 teams was more than 7 points, it actually made the model slightly worse. We went from 75 to back to almost 73% predictive power. So kind of seems counterintuitive if you're thinking about this. If you're thinking about this from the perspective of the game, knowing that your opponent is in a 2-score situation, you would think they are more likely to throw, but the model here wasn't bearing that out. I don't know if that's just noise, or maybe it could also be what the defense was giving them on the play, where the defense is now playing to not give up the big play. And so it may be more effective to just take the rushes that they give you. Or maybe that 10-minute window was incorrect. Maybe it needed to be 5 or 8 minutes. Or it just wasn't worth the predictive power, knowing that the 4th quarter of a 2-score game, you're treating that whole time frame differently. So to me, that was kind of a surprising output, knowing what I know about football and how they treated it. But like I said, maybe it's just from the technical perspective, Quarter's already giving us the most out of that information, and we're just adding confusion into the model once we create that flag for it. So curious outcome. And then we did see, as we're adding more fields to this model, that the random forest and the SVM were starting to catch up to it in terms of predictive power. We saw the SVM at the beginning of the session was at like 68%, I think. Now it's up to 74, which is right behind where we are with the main model. And then random forest is up to 73.8% as well. So I'm going to look through the fields for more things that we can add to it for next time, just to try and get a better idea. Oh, we still have to we still have to go back to the original plays and figure out not necessarily that it was a play with a reception, but a passing attempt. To know the difference. Because if they, right now we only have when a player attempts a rush, which is straightforward, you either run or you don't run, or complete a pass, but we need to change that to be that they attempt a pass. So that's what we'll start with next time. I will try and find more fields out of that data set that we have pulled to try and get a better idea of, or try and get some fields that will hopefully provide a little more predictive power to the model. The goal here is we want to get up to like the 80%, 90% range. Otherwise, the model just may reinforce a lot of the gut intuition you get kind of as a coach or a player in a game, just kind of knowing the situation. So all in all, good progress today. We went from 73 to 75% in terms of the model. I'd like to get up to 80%, but we do also have to see, because I'm not treating it fairly. We are doing only the plays where there are receptions versus plays where are all pass attempts plays. So this is a good place to go for next time. But that's all for today. And then I'll try and probably do a stream over the weekend. It's a holiday weekend, so tough sledding in terms of finding a time to do this. But we did make more progress. We have about, we've got 5 weeks left. Where's the calendar? 1, 2, 3, 4. Yeah, we've got 5 weeks left to put it. We are not quite 2 weeks into this. And it's not like we're, maybe 8 hours total in terms of what we're putting together here, but we've already got a pretty decent model. Spending a lot of time talking about like what we're going to do. If you were going at this purely from like an attacking standpoint, then we're making we're making progress very quickly, and then just trying to find other things that will be useful to add in as we go, and hopefully provide some insights. We may also want to, once we've got it changed to passing attempts, potentially even look at like individual players on a play and see how they are defending or guarding on a play, to see if there's anything that we could key in on whether a play would be like a rush versus a pass play, right? Because right now we don't have the player information here. So who's on the field during a play may also matter. It will definitely matter in an individual game. But as far as the model goes, this will make it take much longer, which is why I wanted to kind of hold off on doing that for a little while. And because your data set's going to become very sparse, is the word for it. You're going to have a lot of rows listing out all the individual players on a play, and then trying to mark whether they're on the field during a given play is also going to be a challenge. So we may want to find a way to limit that. Like, let's say for each team offensively, limit it to maybe 15 to 20 players. I'm just trying to think of like, I know there's 12 players on the field. Sorry, 11 players on the field. Sometimes running backs, tight ends, receivers change. But if we do it for every single player that has played, it would get very wide. Even if I limit it to 15 to 20 players a team times 30, now you're adding 450 to 500 fields to the data set. So, let's not call them fields, columns to the data set, which then makes it take much longer time to do that. And we couldn't use like the one-hot encoding for it. Theoretically, we could if we include the player name. But the way our data set is structured right now, we have a line for each. We have a line for each play in each game. and then the player who had touched the ball. We're not actually providing the player's name, but it would be a change in structure in our data set to incorporate that. So that's why I wanted to kind of hold off on doing that, because that will be a bit of a challenge. Probably would spend the better part of a stream or two. So you're talking anywhere from, I'd say, like 2 to 4 hours just making that change. But then that allows you to make a number of different model types that you would want, not model types, but a lot of different predictions for what you would want to do based on that information. Another idea, as I kind of think out loud, is we're only looking at the offensive side of the plays. We're not looking at all at what the defense is doing, right? So the inverse of this could be true, right? We're looking at just the offensive information and trying to predict run versus pass, but what about what the defense is set up in? Does that tell us anything more about the outcome of the play? With our audience, in terms of these being like the team, members of the team staff, it would also be worthwhile to say, hey, when you guys were in, when you guys were in the empty backfield versus this defensive set, where it was a 4-3 front, or you had like a nickel package, that means that there are 5 cornerbacks. You guys were actually more likely to pass, and here's the rates at which you did that. That information would be another way we could go through this as well. So anyway, that's just a couple ideas off the top of my head on things that we could do for next time. I'll put some more thought into what exactly we're going to do for the next stream, and I'll hopefully be this weekend. If it's not, then I'll be back here Monday afternoon. So for those who are seeing this, hope you all had a happy Thanksgiving, and stay safe out there.